Okay, hello everyone. Welcome to Rasayan Academy. My name is Jagriti Sharma and I have qualified CSIR net exams thrice, and these are my ranks as you can see in the December 18, June 18 and December 17 exam. So guys, I have made a video on, I've already made two videos. One was on the basic of spectroscopy, and the other video was on the Lambert-Beer law. So today we are going to start with the UV visible spectroscopy in detail, and first of all we are going to study some theory on it, and then we are going to see that how the structures can be determined by using the UV visible spectroscopy. So today's class is going to be beneficial for the BSc and MSc students, and definitely students who are preparing for the CSIR net exam, GATE chemistry exam, TIFR, BARC exam and IIT JAM exam as well. So let's quickly begin with the class. Alright, so let me also tell you a little bit about myself. I'm also an educator on the Unacademy Plus platform. So if you go on the Unacademy website, or let's say if you download the app, then you can look for Jagriti Sharma and you will get this preview of my profile, and you can follow me there for regular updates of my free courses and free special class, free live classes and so on. So guys, these are the if you look at this option, these are the free courses which I have made, and these are little videos like just like this that we have on YouTube, and they are definitely free for everyone to watch. I would suggest you to go and watch them, so that there are a lot of previous year questions solved, and you will also be able to access the special classes. So these are all the free recordings. These are all free live classes, and you will see the recorded classes which will be there on the platform. So I would suggest you to watch them, because there are a lot of previous year question videos that I had made on covering mostly a lot of topics on on the organic chemistry as well as the inorganic chemistry as well. And if you want to subscribe to the platform, this is my code Jagriti S, and if you are using this code for subscription, any of the subscription package, you are going to get a 10% discount on the same. Alright guys, so let's quickly begin with the class. Yeah, so we are going to see what is a, basically first of all we are going to begin with the instrumentation part, because it is very important, and sometimes very very simple questions in the exam get asked and we get confused that how to answer this question on the instrumentation. So first we have to know a little bit basic, we have to clear our basics on the instrumentation as well. Okay, so let's first study about the double beam UV visible spectrometer. Alright, so what is a double beam UV visible spectrometer, which is most typically used in the laboratories? Alright, so this is our whole system that I have over here. Now what are the different things that we are using over here? First of all, we have a radiation source, then a monochromator, then a beam divider, and the beam divider, as we can see, is dividing the beam. It is passing through a sample, and it is also passing through a reference sample which is blank actually, and then there's the detector, amplifier, and finally the recorder. So we are going to see what are they made of and what are their what are they doing. So let's first start with the radiation source. So our radiation source can be of three types. So the first type can be a hydrogen discharge lamp, and the hydrogen discharge lamp is giving the radiations in the UV region. Okay, so it is 180 to 400 nanometer. Alright, so this is our first, let's say this is one of the options. Then we have a deuterium discharge lamp, and this deuterium discharge lamp is also discharging the radiation in UV region only, the same region, just that the intensity is 3 to 5 times higher than the hydrogen discharge lamp. Okay, so then it becomes a better option as compared to the hydrogen discharge lamp. And then we also have one more option, which is the tungsten filament lamp. Okay, so this is basically our tungsten filament lamp, and we know that the tungsten filament lamp emits in the visible region. So this is our visible region, and this lamp is going to emit in the visible region. So radiation source can be used depending on our criteria, that we wanted in the UV region, we want to detect a sample in the UV region or in the visible region. So we have these three options for the radiation source. Alright, then we have next is our monochromator. So what is the monochromator doing? Okay, so the monochromator is actually it basically consists of some prism or grating which is actually continuously dispersing the radiation, and it is going to give us a particular wavelength of radiation. Okay, so it is basically dispersing the radiation to give us a single wavelength. All right, and what is it made of? It is made of either a prism or a grating, which must be made of quartz, which is not made of glass. It is not a glass prism because glass is going to absorb in the UV region, so it must be made of quartz as it is transparent in the UV region. Okay, so if you want to detect some sample in the UV region, we need to take quartz prism or grating, and if you want to detect some sample in the visible region, then we can take glass because glass is going to absorb in the UV region. All right, then we have a beam divider. So what is the beam divider doing? As its name suggests, it is dividing the a single let's say monochromatic wavelength beam which is coming out of the monochromator into two equal intensity beams. So guys, the reference beam and the sample beam are going to be equal intensity beams, and one of the beam is passed through a blank sample. Okay, and check if they are this is basically for cross checking. Okay, and one of the beam is passed through the sample, and the sample is going to absorb some of the UV radiation, and then it is going to transmit some of the UV radiation. Okay, so here is our sample detector. So some of the radiations are absorbed by the let's say it is I, it is absorbed, and let's say this is our I naught, because this is just going to be the same. There is no absorbing element over here. It is just going to come over here like this. So we have a sample detector, and what is the detector made of? So basically the work of a detector is to detect the radiation that is left, or let's say transmitted by the sample. So how to detect the radiation? So detectors must have the photocells or photomultiplier. Okay, definitely light sensitive stuff. So photocells or photomultiplier tubes are going to work by generating voltage which is proportional to the radiation falling on it, which means as the intensity, if the greater the intensity of the radiation falling on it, greater is the voltage produced. That is how the detector is working. All right, then this the detector is passing the signal to the amplifier. So the amplifier, there is a balancing amplifier which electronically subtracts the absorption of solvent from the solution. So basically it is also working as the amplifying the sample the solute or the sample signal by subtracting the absorption of the solvent. So it is working to amplify the sample signal. And then finally there is a recorder which is going to give us this graph like this. This is our molar absorptivity coefficient, and this is our wavelength. So this is how we get the lambda max for any sample over here. So this was basically the working of our double beam UV visible spectrometer, and I hope this is a very basic representation, but it does the work of explaining the basics. And these are the types of radiation source, the monochromators, and these are the functions of the detector, the amplifier, recorder, and so on. So now what we can do is we can now jump on to the theory part. Okay, so first, before that, we have sample handling also. That how are we going to use the sample? It can be a solid sample, liquid sample, gaseous sample. How are we going to check the UV spectra for that? Okay, so in the sample handling, we are just going to see that UV visible spectra, it is usually recorded in very dilute solutions. Okay, and also in the vapor phase. So basically UV visible spectra is recorded in very dilute solutions or in vapor phase. So if there is a molecule, if there is a sample which is solid, so first of all we have to find some solvent to dissolve it, and we have to make a very dilute solution. What is the other criteria? The cell which is used must be of quartz, because we had just talked that the glass is going to absorb in the UV region. So the quartz cell must be used, which is a 1 centimeter square. Okay, the area is a 1 centimeter square, and this is commonly used for the UV visible spectroscopy. Then what we have is the sample is dissolved in a solvent which does not itself absorb the radiation in UV region. So basically, if we are using some solvent to dissolve our sample, let's say solid sample or liquid sample, to make a very dilute solution, then the solvent must not absorb in the UV region because it is going to hamper the final result. So such solvents that we can use are cyclohexane, 1,4-dioxane, water, and 95% ethanol. So basically, yeah, we see the lambda max of all these species over here. These are our solvents, and these are the lambda max value. As we see over here, cyclohexane is having absorption, UV absorption as at 210 nanometer, 1,4-dioxane at 215 nanometer, water at 191 nanometer, and ethanol at 210 nanometer. So basically guys, we can very safely observe our UV spectrum, UV visible spectrum, because the UV range is 190 to 300 nanometer, or let's say it, if you want to remember it nicely, then you can also write 200 to 400 nanometer if you want to remember it better. So it is not falling, or let's say it is very much closer to the ultraviolet end over here, and it is not going to disturb much if we want to, let's say, cover our spectrum from, let's say, 200 to 800 nanometer, as which is there in the UV visible range. So basically after 250 or after 220 nanometer, none of these solvents are going to disturb the UV spectrum. So they are the perfect solvents which can be used for checking the UV visible spectrum of a salt. Alright, now let us also talk about the electronic transitions. They are very important. So now if we want to go deep into studying the spectrum, if we want to analyze the spectrum, we have to first of all know that what are the electronic transitions. So the basic electronic transitions which show are given over here. Alright, and let me also tell you that what are we are talking about organic spectroscopy, right? We are talking about organic molecules over here. Then what are the possible the bonding levels which are possible, bonding and anti-bonding or non-bonding levels. So these are the levels. One is the sigma state, the other is the pi state, and other is the non-bonding state. So basically guys, we know what is a sigma bond and a pi bond, we know that. So if there is a sigma bonding orbital, there must be a sigma star anti-bonding orbital. If there is a pi orbital, there must be a pi star anti-bonding orbital. What about the N? The N is for the lone pair. Okay, so whenever we have, let's say, a carbonyl bond like this, so these are the lone pairs over here, and this comes in the non-bonded electron pair, or let's say the non-bonded state. So these are the transitions, various transitions which are possible. So one is our sigma to sigma star transition, where the sigma, electronic transitions are happening from sigma to sigma star level, and as we can see, this is the longest line, which means this is the highest energy transition. So this is our highest energy transition. Then we have N to sigma star, which is the non-bonded pair electron being transferred to the sigma star orbital. So this is also high in energy but less than sigma to sigma star. Then we have pi to pi star, okay, here, and then we have N to pi star. So basically these four are our basic and the most important and most noted transitions in the UV visible spectroscopy. And in which compound are they found? See, the sigma to sigma star transitions are very high electronic transitions, and they are found only mostly in alkanes, because in alkane there is no pi bond, there are no lone pairs. So in alkane, sigma to sigma transition is only possible, and they fall in this wavelength region, 122 to 150 nanometer. It is purely UV. Okay, they're not falling under UV visible region, it is higher UV region. Alright, so that is why sigma to sigma transitions are not very easily recorded in the range that we are studying for our organic compounds, for let's say colored compounds and so on. Then there is our N to sigma star transition, and it occurs in alcohols and haloalkanes. So basically In alcohols also we have a lone pair, in oxygen. In haloalkanes also we have a lone pair, let's say any halogen that we take. So this is the non-bonded electron pair going, the electron transition taking place from non-bonded electrons to the sigma star, which can happen in alcohols and haloalkanes. And these are the regions. For alcohol it is 183 to 190 nanometer, for haloalkanes it is 170 to 260 nanometer respectively. Alright. Then we have the most important and the most studied transition is the pi to pi star transition, because it can very it is mostly studied in the compounds when there is unsaturation. It can be carbon carbon double bond, carbon oxygen, carbon nitrogen, and so on. There must be unsaturation and a pi bond to be able to study this band over here. Alright, and it occurs in compounds with a pi bond at around 160 to 170 nanometer for simple alkenes. So if we talk about simple alkenes, then this is the region 160 to 170 nanometer. But if we talk about carbonyls, then it is 180 to 190 nanometer. Okay, for carbonyls, and definitely this is going to happen because there is an oxygen connected over here. Alright. Okay, so yes, these are the basic electron transitions. Let us also talk about the N to pi star electronic transition. It is, as we can see, it is the lowest energy transition, and it is studied in carbonyl compounds mostly at around 200 to 300 nanometers. So as you can see guys, this is having the lowest energy and the highest wavelength. Alright, 200 to 300 nanometer. Okay, N to pi star. Definitely we are having a, we are having in a carbonyl we are having the lone pair, and we are also having the pi star. Alright, so N to pi star is very frequently studied in carbonyl compounds. Okay, let us also get accustomed with some of the major terms which are used in the UV visible spectroscopy, and they are the chromophores and the auxochromes. So guys, what is a chromophore? A chromophore is a group basically which is actually absorbing, it is giving the main absorption spectrum. So it is very yeah, it is a group which is responsible for absorption in the UV visible spectrum. Alright, so what is a chromophore? Let us see some example. Let's say we have a molecule, let's say we have benzene. So in the benzene, the major absorption is because of the carbon-carbon double bonds that we have. Alright, so chromophores must have unsaturation, and the unsaturated groups are mostly the carbon-carbon double bond, the carbon-carbon triple bond, carbon-oxygen double bond, carbon-nitrogen triple bond, nitrogen-nitrogen triple bond, and so on. The list is endless, right guys? So basically there must be unsaturation in the group, and that unsaturation is going to give you a very good color. Alright, however, they will only impart color if they absorb in the visible region. Okay, because if they are absorbing in the UV region, then they are not going to transmit any radiation in the visible region. So basically they are not going to show us color. Alright, also different chromophores correspond to different colors. Definitely benzene is going to have a different color. Let's say we talk about aniline, it is going to have a different color, anisole is going to have a different color, and so on. Alright, then there is one more thing. This is the auxochromes. So basically the auxochromes are supporters of chromophores. The chromophores are the main group responsible for absorption, and auxochromes are basically going to increase the absorption somehow. So let us see the auxochromes. When in a compound, the hydrogen atom is replaced with some groups which increase the intensity absorbed and also the wavelengths. So basically the auxochromes are increasing the absorbed intensity as well as the wavelengths, and they are called the auxochromes. An example of such auxochrome groups are NH2, OH, SH, carbon-carbon double bond, and so on. So as you can notice from here, the auxochromes must have electron-rich carbons, electron-rich center. Basically it must have a lone pair, or let's say a pi bond, by which it can donate the electron pair to the chromophore, so that the electron density increases. And if the electron density increases, then definitely the intensity of light absorbed will also increase, and also wavelength will increase. Okay, alright, why is the wavelength increasing? We are going to study that in the next slide. Alright, so yeah, so this is a whole, these are the most important terms that we can use to describe the UV visible spectroscopy, and let us understand them one by one, because this looks a very busy slide over here. So let's only focus on this graph. This graph is intensity versus wavelength. Let us only focus on this graph for a while, only this portion. Yeah, only this portion. So if we look at the if we look at the peak over here, let's say this is our one of the samples that we are detecting, and this is the peak that we get. All right, so if we are getting this peak, then we can say that this is our lambda max, because this is the wavelength in the x-axis. This one is our lambda max with the intensity this much. All right, now what happens if we have a molecule like this? If we have plain benzene, and if the lambda max of plain benzene is 256 nanometer, so let's say this is our benzene peak, the peak is for benzene and the lambda max is 256 nanometer. Now if we are adding an auxochrome to benzene, let's say, yeah, benzene is our chromophore and NH2 is our auxochrome. So if we are adding NH2 auxochrome to benzene, then we can very easily say that because of resonance, the electron density has increased. Okay, the molecular orbitals have extended and the electron density over the whole molecule have increased. That is why the intensity of absorption will also increase, as well as the wavelength also increases. Okay, so basically it is called bathochromic shift or red shift. Why red shift? Because the lambda, let's say the wavelength is going towards red. Okay, so if the lambda is increasing, we call it the bathochromic shift or the red shift. Just now we have talked about the addition of a chromosome, how auxochrome, how is it affecting. So addition of the auxochrome is going to increase the lambda max, and it is called a bathochromic shift. All right, what if we talk about just opposite of this? We are just increasing resonance over here. What if we decrease the resonance? All right, what if we decrease the resonance? So if we decrease the resonance, let's say we have aniline, and the aniline is showing absorption is at 280 nanometer. Now if we are adding, let's say we are adding some acid to aniline, definitely the lone pair of aniline is going to take up the acid to give us this quaternary ammonium salt like this. So now there is no more the lone pair available and the resonance has stopped. So if the resonance has stopped, the only electron density is there in this benzene ring, and because of the minus I effect of the quaternary ammonium salt, because of its minus I effect, what happens is again the electron delocalization has decreased. That is why the wavelength has become 254 nanometers. So wavelength has decreased. Alright, so if the wavelength has decreased, we call it blue shift, because it is going more towards the violet region, or let's say the blue region. Okay, and that is why the shift is called a hypsochromic shift. Alright, so if we see it on the graph, this was our lambda max for benzene, or let's say, yeah, any compound. If we are increasing the conjugation, then it is going towards a red shift and the wavelength is increasing. If we are decreasing the conjugation, it is going towards blue and the wavelength is decreasing like this. So even if you try to, if you try to compare the quaternary salt of ammonia, aniline and benzene, you will see their wavelengths are almost similar, even though benzene has a greater wavelength 256 nanometer than the quaternary salt of aniline 254 nanometer. So basically, because of the removal of resonance as well as because of the presence of minus I effect, this has become even less of a less of a conjugation as compared to benzene. Alright, so these were bathochromic shift and hypsochromic shift. What about the shift in intensity? Yes, there is also a term for the shift in intensity. It is the hyperchromic shift, in which the intensity is increasing. Yes guys, this is the intensity increasing over here. Then we have hypochromic shift, in which the intensity is decreasing like this. Okay, so Definitely we had talked about that how is the intensity increasing if we are adding some auxochrome. If the resonance is increasing, the intensity is increasing, and also the wavelength is increasing. How do we see the intensity? We see the intensity by the absorptivity coefficient. So for benzene it was 200, and this is pi to pi star transition, guys. For benzene this is 200, and for aniline it has become 1430. So there is a drastic increase. All right, more than 7 times. All right, so this is the drastic increase in intensity is giving us the hyperchromic shift. All right, and similarly, if we try to have more examples, if we try to see, then what we can see is we have a system called biphenyl. So here we are going to study the decrease in intensity. Okay, so let's see the intensity of biphenyl as such. So biphenyl is a it is a, both the planes are not both the rings, benzene rings are not in the same plane, they are a little bit twisted. Okay, all right, this has lambda max 252 nanometer, and the absorptivity coefficient is very high, 19,000. It is really high. Okay, so one of the intensity has increased hugely because there are two phenyl groups like this. Okay, so if we are giving substitution, if we are adding two methyl groups to the ortho position like this, so these are the ortho position of the two benzene rings. So because of the steric hindrance, what is going to happen, the rings are going to turn out of the plane, they are going to turn perpendicular to each other, and there is a complete disruption of the pi bonds, which pi interaction which was taking place between these two rings. So because of the complete destruction of the pi bonds, the electron the absorptivity coefficient epsilon max has now become only 800. So it has gone down, the intensity has gone down from 19,000 to only 800. Guys, you can see the difference. Okay, so the lambda max has also increased to 70 nanometer, and however there is a huge drastic change in the intensity because of the twisting out of the plane. So that is called a hypochromic shift now. Intensity has decreased. Okay, so I hope that you are all clear with the bathochromic hypsochromic shift in the lambda, or let's say the wavelength, and also the hyperchromic and hypochromic shift in the intensity. Okay, so these are some of the examples that you have to remember, and most of the times these fall under the category of effect of conjugation on the absorption pattern, the effect of pH on the absorption pattern, and the effect of steric hindrance on the absorption pattern. So basically what I did was I showed you the examples of these four cases, and then I also classified these cases under the effects, factors affecting the wavelength, the effect of pH, effect of steric hindrance, and the effect of conjugation. All right, quickly let's also see that what is the effect of conjugation on a molecular orbital level. Okay, so basically I've drawn the orbitals over here, and let us also see what happens. So guys, let us look over this right part over here, this part over here. What is happening over here, as you can see, is if we are taking an ethene molecule, a simple ethene molecule which has only one double bond, one pi bond. So if we are having one pi bond like this, then there must be one of these must be the pi bonding orbital, in which both the p orbitals are in the same plane like this. There is no node, so this is our homo. All right, psi 1. Then the other possibility is of an anti-bonding pi orbital. So this is our pi bonding orbital, this is our pi anti-bonding orbital, pi star basically. All right, then here is a node over here. So in this molecule, in this orbital, molecular orbital, there is a node. The plus has gone opposite like this. So this becomes our lowest unoccupied molecular orbital, and the pi bonding, for because there are only two electrons in one pi bond, so it is our homo. So as we can see, there is only one pi bond over here. What if we talk about butadiene system? If we talk about butadiene system over here, it has two pi bonds. Yes, so if it has two pi bonds, then these are the depictions of all the levels it has. So the first one is our psi 1, the first molecular orbital depiction is psi1 is having no nodal plane or no node, and all the orbitals are in bonding phase. All right. In psi2, which is higher in energy, there is one nodal plane like this, and these two, let's say these two are in the same phase and these two are in the same phase but different from these two. So basically here is one nodal plane. In psi3 there are again two nodal planes, and this is a very simple diagram, guys. There is plus and these two are minus, then again there is plus. In psi4 there are again three nodal planes. So the nodal planes depend upon the number of orbitals we are having. If we are having 4 orbitals, then we are going to have n minus 1 nodal planes. So if this is psi4, we are going to have n minus 1, 4 minus 1, 3 nodal planes over here. So alright, so these are our system basically for the butadiene system. Alright, so now as we can see, the transition must go from the HOMO to the LUMO, which means the occupied to the unoccupied level. Definitely the electron transition is going to take place from the occupied to the unoccupied level. Yes. So when there was only one bond, the energy difference was huge, and with greater conjugation, when there are two pi bonds, the energy difference is not very huge. The HOMO and the LUMO have come together. Alright, they have come closer to each other like this, and as a result the energy is decreasing. So as we can see in these examples, as we are going on increasing the number of pi bonds, the HOMO-LUMO gap is actually going on decreasing. So guys, basically here the HOMO-LUMO gap is the least in this one, because there are how many pi bonds? 1 2 3 4 pi bonds over here. So this has the least let's say energy difference, and that is why it is going to have maximum lambda max value, because the energy is inversely proportional to lambda. Greater the energy, smaller the lambda, and smaller the energy, greater the lambda. And that is why on increasing conjugation the wavelength shifts towards red. That is why it causes a greater shift to wavelength, or the wavelength increases, causing the bathochromic shift. I hope that this is all clear to you, because we have talked about a lot of stuff, and in the upcoming classes, in the upcoming lessons, we are going to study about the lot of stuff. Yes, about the Woodward-Fisher rule to calculate the wavelength for the different alkenes, different systems. So we are going to talk about that a lot, and we are also going to see some previous year questions as well from the CSIR exam. Alright guys, I hope that you were able to understand this video, and if you like it, then please also share and subscribe. Thank you very much for watching.